All right, the first example we have is there is a piston cylinder device that contains 2 kilograms of water at 1400 kilopascal and zero point 0.9 quality. Now heat is transferred to the system. During this constant pressure process, the volume triples. Calculate the heat that must be transferred. Okay, so let's start with sketching and analyzing our problem. So we have a piston cylinder device. We identify our system as water. This is very important because we need to look at water tables. It tells you to look at water tables. And they give us the mass to be 2 kilogram. And remember, for closed systems, the mass is not going to change throughout the process. Besides that, they tell us that the initial pressure is 1400 kilopascal and the initial quality is 0.9. That also means by giving quality, they are telling us that this is a mixture. All right, and there is another information. The volume triples means 3 times the first volume is equal to the second state volume. All right, you can also write it 3 times of the specific volume at the first state is equal to the specific volume at the second state, since volume is equal to mass times specific volume, and we know that mass is the same throughout the process. All right, so what they're asking for? They're asking for us to calculate the heat. That means I need to write energy balance, because heat as a term exists in the energy balance, and if I want to find heat, then first I need to write my energy balance correctly, then figure out how I can calculate the heat from the energy balance. And now I need to analyze the system carefully and figure out what type of energy interactions are there. First of all, we know that there is heat transfer to the system, but they don't say anything else. But we understand in a piston cylinder device, when there is expansion like this, the piston is pushed by the system. So when system pushing the piston, it's losing its energy. So we are talking about expansion, we are talking about boundary work. So besides the heat interaction, there is boundary work getting out because the system is doing the work. So start with writing the general form of the energy balance. For a closed system, energy getting in minus the energy getting out is equal to the change in the internal energy of the system. And then let's look at what type of energies are getting in. And we know that for a closed system, there are only 2 types of energy interactions, heat and work. In this case, we are seeing in this problem, we are seeing just heat getting in. Okay, so this energy balance will be different based on the problem, right? So for each problem, we need to write down the correct energy balance. So in this problem, only heat is getting in. Nothing else, nothing, work is not getting in. There's nothing else getting in, but there is a work getting out. So I say minus the boundary work out. And this is equal to internal energy change. And if you remember that for a constant pressure process, you can actually combine the internal energy change with the boundary work getting out and write this in terms of the enthalpy change, right? So this means m times H2 minus H1. So this is your energy balance, all right? And I can use this to calculate the heat interaction. Do I know the mass? Yes. So if I want to calculate the heat, I need to figure out what H2 and H1 is. And the way to figure those out is to look at the tables and read the properties, specific properties from the tables. And let's take a look at which table we need to look and to read these properties and analyze each state carefully. Okay, so for state 1, we are given the pressure. We are also given the quality. Sorry, it's 0.9. All right, and let's see if we can calculate what H1 is. First of all, by giving you quality, that means they are telling us it's a mixture, right? This tells you that you have a mixture, so there is a phase change going on. And if you have a mixture, we know that only way to calculate a property, a specific property of a system, is through the use of this equation, right? Which utilizes the quality. So H1 is equal to HF plus the quality times HFG. Okay, so now at 1400 kilopascal, when you have a mixture, you can go to the table A5, which is for water, but when the pressure is given, the pressure is 1400 kilopascal. I can read HF and HF here, HF and HFG from there, and plug into my equation and calculate the first state specific enthalpy. All right, let's do that. So H1 is equal to 829.96 plus 0.9 times 1958.9. So your specific enthalpy at the first state is 2592.97 kilojoule per kilogram. Okay. All right, so that we can now use this in our energy balance. Right? And next, let's look at how we can calculate H2. Can we check the tables to see if we can read H2? They are telling us the pressure at the second state is 1400 kilopascal, but they are not giving us any other intensive property so that we can look at the table and read H2. So here you need to think carefully. Does actually problem giving me any other specific property for the second state? And if you look at it carefully, you will see that you can actually figure out what is the specific volume at the second state. Because since you are given the quality and you can use the equation which relates the quality to specific volume at the first state and calculate the first state specific volume from there, and we know 3 times of that specific volume at the first state is going to be equal to the specific volume at the second state. So use the quality equation. Quality is equal to V1 minus Vf over Vfg. Remember, Vfg is Vg minus Vf. Okay, so you go to the same table, but this time you read Vf and Vg and insert these numbers to your equation, right? And calculate what is V1. And specific volume at the first state is 0.1268. And specific volume at the second state is 3 times of that. Okay, so you can plug this in here, that you know it is now we are given the pressure, and we figure out that they are actually giving us the specific volume at the second state. Now we can look at the tables to read what the second state enthalpy is. But to be able to do that, first you need to figure out which tables to look at. So again, always start with the saturation tables and see at 400 kilopascal what is Vg and Vf, and compare your number with Vf and Vg. And if you do that, you will see that your specific volume is actually, remember, 0.3804, which is bigger than Vg. That means that actually you have a superheated vapor. Okay, so you first conclude that you have a superheated vapor. And now to be able to read what the specific enthalpy is, you need to go to table A6, which is the superheated vapor table. Okay, where is it? This one. Okay, and our pressure is 1.4. It is 1400 kilopascal, so 1.4 megapascal here. And then we look at they're asking us to calculate the enthalpy, and what we can do is use the specific volume to calculate the enthalpy. So our specific volume is 0.3804, so somewhere in between, right? And then the enthalpy should be somewhere in between these numbers. That means that you need to do linear interpolation. So take these numbers and do your interpolation. So let's do that linear interpolation in another page here. Okay, so we read specific volumes and then specific enthalpies from the table A6 and doing linear interpolation. So for a specific value of 0.35288, we read from the table that specific enthalpy is 4,154.3, and for a specific volume of 0.38614, the specific enthalpy we read from the table is this. And for the specific volume of 0.3804, what is the specific enthalpy? That's what we're gonna calculate from linear interpolation. Let's do that. 0.38614 minus 0.35288 over 4,393.3 minus 4,154.3 is equal to this minus that, right? 0.38614 minus 0.3804 and is equal to this minus that. Okay, so H 4,393.3 minus H2, and H2 is gonna be 4,352.053. kilojoule per kilogram. So the way to make sure you did it correct, the number should be in between these numbers, right? In fact, that is correct. So all you have to do is now plug this information in the mass, in the energy balance, which was mass times H2 minus H1. All right, and you end up with 3,518.2 kilojoule. Make sure the units give you kilojoule at the end because that's the energy unit, right? So here is your heat interaction that you were looking for.